In this video, we're talking about one more feature of graphs known as concavity. Graphs can either be concave down or concave up, or a mixture of both. I have two examples here that we'll take a look at. Let's take a look at this one on the right. This graph is concave down in the first region, then it reaches an inflection point where it changes to concave up. What do we mean that the graph is concave down? Well, in the simplest way of thinking about it, it's a U that's opening downward. If you tried to pour some water in here, it would fall right out. Over here, where it's concave up, it's a U that's opening upward. If you tried to pour some water in here, it would actually fill the bottom of this piece of the graph. This gets a little more confusing when it's not as clear of a U, but it can still be concave down and concave up, like this graph on the left. On the left side, it's concave down because you can imagine this is part of a U shape, and this would no way hold water or anything like that. And on the right side, it does change to concave up, even though it's not so clear that it's a U shape. So the simplest explanation is that it's a U shape opening down or a U shape opening up, but the reality is that it just needs to be a general curve upward or a general curve downward to be concave down. In a graph, if it changes from concave down to concave up or up to down, this point is known as an inflection point. Let's get a more rigorous mathematical definition of concavity, whether a graph is concave up or concave down. To know whether a graph is concave up or down, we must look at the second derivative, or f double prime of x. If the second derivative is greater than 0, we say that the graph is concave up in this area. If the second derivative is less than 0, we'll say that the graph is concave down in a certain area. If the second derivative is equal to 0, this is an inflection point where the graph is changing from concave up to concave down, or vice versa. Let's take a look at the function f of x is equal to x cubed minus 6x squared minus 12x plus 2. We're going to find where the graph is concave up, concave down, and any inflection points. Well, looking at our definitions for concavity, we're going to need the second derivative. So let's start by finding the second derivative of this function by first finding the first derivative, then taking the derivative one more time, and we'll start by trying to identify any inflection points. So we'll take this derivative, second derivative, and we'll set it equal to 0. At this point, we'll add 12 and divide by 2, so we have x equals 2. This is a potential inflection point, and we'll know if it's an inflection point if the graph changes from concave up to concave down or from down to up. If it doesn't change from up to down or down to up, this is not an inflection point. So how are we going to test this? So we'll label this as a potential inflection point. And we need to test the intervals. So we'll set up our number line and we'll say 2 is a potential inflection point. But what is the second derivative doing on the left side? And what is the second derivative doing on the right side? Is it concave up here, concave down here? What's going on? So we'll just test some values, very similar to what we did with the first derivative when we were trying to find increasing and decreasing intervals. So let's test 0. F double prime of 0 is 6 times 0 minus 12, and that equals negative 12. So it looks like to the left of 2, the value of the second derivative is less than 0 or negative. Let's test a value to the right. Let's test 3. Looks like we're going to have 6. So to the right, the value of the second derivative is greater than 0. So looking back at our definition, we would say this graph is concave down to the left of 2 and concave up to the right of 2. So at 2, there must be an inflection point because the graph changes from concave down to concave up. Let's take a look at the graph of this function just to make sure what we found out can actually be confirmed by a graph. We expect it to be concave down to the left of 2 and concave up to the right of 2. So looking at this graph, it looks like it's concave down, like it's a U shape opening down all the way until 2. And then at 2 is the point of inflection where it changes from concave down to actually being concave up for the rest of this graph. The last thing we want to do is just list the intervals where it's concave up and concave down. For this graph, we would say it's concave down from -infinity to 2 using parentheses, because at 2 it's neither up or down, it's actually equal to 0. And we would say it's concave up from 2 to infinity.